This is CPE 233. This is lecture 23. What we're going to talk about is the timer counter module, and which is what module we use in experiment 9. And then we won't do an example problem. We will save that for another video. So when you talk about blinking something, there's two possibilities here, and essentially it's the rate at which you blink it and also the duty cycle. So we don't necessarily need a 50% duty cycle when you blink something. When the blinking LED is a classic hello world of embedded systems. Essentially, if you can get an LED to blink, that means you've got your hardware talking to your software, etc., etc. Typically, I know it sounds kind of wimpy, but it's actually very effective to get an LED blinking. Two approaches to doing anything in digital land with a microcontroller in your system. You can have the microcontroller do the work, which means executing instructions, or you can offload that task to some external module. So the timer counter that we're going to talk about in this experiment is an external module that allows the processor, gives the processor freedom to do other things rather than do stuff stupid like count and time things. And you'll see that come up a little bit later. So works really good. Typically speaking, you'll see that oftentimes in embedded land, you need to time stuff or synthesize signals or blink LEDs or generate a pulse width modulation. Timer counters work great for that, and that's why, typically speaking, on a typical microcontroller, you have quite a few timer counters on it. Oftentimes, you'll need to count like the number of events that happen, or you're going to have to measure a certain time period. Both things are done quite easily with a timer counter. For this experiment, we're just going to essentially count events. We're not going to use the counting, or we're not going to use the figure out a delay between events. Yes, extremely common on hardcore microcontrollers. Oftentimes, even a low-end microcontroller has quite a few programmable timer counters. These timer counters have large feature sets. Ours is very simple. It allows, essentially, once again, it allows you to do a whole bunch of stuff in the background. And that's going to free up the processor to do more meaningful things. And these are devices that are programmable via registers. So what you're going to do is, they're not executing code, but you're going to program like a control and status register such that that register controls the timer counter in the way you want it. Very flexible. Even our simple one in this experiment is quite flexible, but nothing like what you find on a real microcontroller. So this is our timer counter module. Inside this thing, there's actually 3 registers. One is the count. We'll call this the terminal count, and then this is the CSR register. So that there's a counter in here, and what I'm going to do is I'm going to be able to write this value, and then this value counts increments upwards. So when this internal counter equals that value I wrote to it, it's going to send out a pulse. I can actually control this by writing to the other register, which is the control and status register, and I can actually at any time read the output of this counter right here. So this is an example of what's happening. If I set that terminal count at this value here, you can see it go from here to here. It hits its terminal value, and what it's going to do is two things. It's going to send out a pulse on the INTR output. It's also going to clear the counter automatically and start counting over again automatically. I don't have to worry about any of that. It's programmed. The hardware is designed to do it that way, and works quite nicely. So once again, there's the timer feature in here. Essentially, there's a register that holds a terminal count, and when that terminal count equals just a normal counter inside this thing, it sends out a pulse. I can actually measure the time of events too by reading the output of the timer counter at 2 different times and subtracting or taking the difference between those readings to give me a time reading. So there's 2 modules in there's two programmable registers in the timer counter. One is the control and status register. So it has two parts to it. One of these bits is just an on-off bit for the timer counter. The other is a prescaler. Now the prescaler the count itself, the terminal count, is a 32-bit register, but I can effectively extend it by 4 bits by programming these 4 prescaler bits. And the prescaler, like an unprescaled clock signal, looks like this. A prescaled clock signal looks like this. And this is the prescale of, we'll say, SPSCL equals 0001. Okay, so as this value here goes up, I lose more signal. So this is once again a way to slow the clock down. We don't really necessarily need it to do it in this experiment because 32 bits is quite a number of bits, and that's going to get us a very slow clock signal if we want it. To figure out how this works, you're going to kind of use this timer counter reference design. I'm giving you the code. I'm giving you the Verilog code for the module, but I'm also giving you the software for a working program. So the first thing you want to do is take your wrapper and put the timer counter in your wrapper and then run this program. Now this program, we'll talk about it in a second, but what it does is it blinks an LED and then it transfers the values on the four rightmost switches to the 4 rightmost LEDs. So that you're going to see this program in a second. It's a typical interrupt-driven program where I got to initialize a bunch of stuff, and then there's going to be a foreground and a background task. Foreground task is essentially going to be the interrupt service routine. The background task is everything else other than the initialization code. This is the reference design program. This is all the initialization code. And what we need to do in this is, because it's an interrupt-driven program, we need to do the typical stuff. So the first thing we need to do, I'll get that back here. First thing we need to do is enable the interrupts. You've seen that before. Essentially, I'm sorry, that's not enabling the interrupts. That is writing the address of the ISR in MTVEC. So when I get an interrupt, that address is loaded into the program counter. Next thing I need to do, which you haven't seen before, is I need to program the timer counter. And so these are the port addresses that I'm going to use in this experiment. This is for the LEDs and switches, but these are for the 2 registers and the CSR, and they're mapped. These are the addresses that the wrapper that you should use in the wrapper. We'll put it that way. So that allows you to write to these registers in the timer counter. It does use an LED, so I'm going to clear that register to start off with. This is a matter of I'm setting a terminal count and I'm writing it, and then I am turning this module on by writing this bit. I'm not turning any prescale bits on. Once I do all that, I'm ready to enable the interrupts, and then it's ready to go. So once again, write the interrupt service routine address into the vector address. Get some initialization of the registers. Kind of clear the starting point of the LED register, and then I'm going to these 4 instructions here are setting the terminal count, and then I'm going to turn the timer counter on, and the last thing I do is enable the interrupts. This is the main program. What this is doing is it is getting the switch value here. Let's get that. Here's getting the switch value, clearing all but the bottom 4 bits, and then I'm adding in the bit 7. Okay, so in bit 7, essentially what I'm doing is toggling bit 7 in the interrupt service routine. So here's the interrupt service routine here. All I'm doing is toggling bit 7. And the issue here, after whatever that bit is, I'm adding it to the LED value and then outputting it. And that's the entire program. So program breakdown, that we initialized a bunch of stuff, and then there was a foreground and background task. Background task being, the adding of the status of the LED bit to the switch bits, and foreground task is simply toggling that bit 7. So all this timer counter package is on Canvas, and there's a user guide which is in the back of the manual. There's also the driver program, and then there's the timer counter module itself, which is Verilog code. It's all out there, ready to go. So experiment 9 has a whole bunch of different parts to it. You want to do part C. Essentially, part C is a redoing of experiment 8. Experiment 8, you debounce the buttons in hardware. Experiment 9, you're going to debounce the buttons in firmware. Experiment 8, you had a dumb delay. You had a delay that used instructions. In experiment 9, you are going to use the timer counter for delay. Once again, that delay is associated with the display multiplexing. You got to use the RARS assembler for experiment 8 and 9 because it uses interrupts. The Venus doesn't handle interrupts. Everything else is the same. You assemble a file, throw the memory over into your auto_memory.mem in Bravado. RARS, there's a package on PolyLearn. Make sure if you're using a lookup table that you choose the both option and the hexadecimal option when you go to dump the file. And this is an example, hardware modification example. This exists in another video, so we won't go over it here. The other video probably does not have the solution, so here's the solution for it.